This twisty helical model, looking like a spiral staircase, represents one, if not the triumph of 20th century science. In this simplified form, consisting of the treads and the two twisted backbones, it does look simple. It is, of course, the hereditary chemical DNA. But 30 years ago, it wasn't quite so simple, so easy, for Jim Watson and Francis Crick, who finally cracked the problem.
Easiest way to answer this is to look at a little bit of the molecule, such as the one I have here, and you can see that we already know quite a bit. These balls represent atoms, the rods represent the bonds between atoms, and we know from the study of small molecules in crystals, this distance, for example, to about 1%, all the other distances, we know all the angles. So it is true that we do know the shape of that little bit. That's a base, and it's connected to a sugar, but it's connected by a single bond. The sugar's fairly rigid too. But what isn't rigid is this bond here. You can get free rotation about it. And there are other places in the molecule where there's free rotation, several along the backbone. So there's a very large number of ways, given the chemical formula, that you can actually build a model.
The kinds of compounds that they were modelling were these. This one's made from your orbit kit. Now the important thing about this particular model is this part, the nitrogenous base. In DNA, there are only 4 nitrogenous bases. They all have a similar shape. We don't need to know their exact structure. We'll just call them A, T, G, and C for short. Each nitrogenous base is connected to a sugar, here, and a phosphate. They found that they could pair these bases so that one base was here and the second base across here joined together through hydrogen bonds. The sugar and the phosphate form the backbone, and they found that by stacking in this way they could get a spiral helix.
And suddenly I could put together A and T and G and C. Could hardly believe it. And Francis came in almost immediately and saw this. And you remember...
We didn't work with a great big model. We worked with a small piece, just a sugar, a phosphate, and half a base pair. And I had to get it so that the bond distances and angles were reasonable. It joined on to the next one, and it was at the right sort of radius, and so on.
But the triumph of DNA wouldn't have been possible if earlier chemists hadn't made models and similarly got it right. In fact, it all started with atoms. At the beginning of the 19th century, John Dalton formulated his atomic theory. He produced a set of symbols for the atoms, but he also produced models of atomic centers, these. We have here some carbon atoms and a hydrogen atom. Using these models and his symbols, he tried to get a formula for ethanol. In fact, he was wrong, but can you see where? The chemist Van 't Hoff had other ideas. He felt it was time that organic chemistry moved into the third dimension. And in 1874, he produced this matchbox set of models to illustrate his theory of the tetrahedral carbon atom. Each of these little tetrahedra represents a molecule, and he's put the atoms at the faces of the tetrahedra. Nowadays, the tetrahedral carbon atom is the cornerstone of organic chemistry. Van 't Hoff put the atoms at the centers of the faces, but nowadays, although it gives a completely equivalent result, we put the atoms at the corners of a tetrahedron. This model shows a carbon atom with, at the vertices of the tetrahedra, 4 hydrogen atoms. Now, what is this molecule? Yes, it's the simplest hydrocarbon, methane. You should be becoming aware now that carbon is a very versatile element. In fact, it's used in biological molecules and man-made molecules. And much of this versatility is built on the tetrahedral carbon atom. In this program, I want to show you how we can use molecular models to illustrate the relationship between atoms in molecules and how we can understand their properties from this, because it's becoming more and more clear in both biological and organic chemistry that the form of a molecule is intimately related to its function. This is a model of a complex organic compound called cholesterol. It's made with a model kit called the FISA kit. It contains some structural features that you've already seen. There's a hydroxyl group and a double bond. The main thing about a steroid is that it's got 4 rings. 1, 2, 3, 4 rings. Now this FISA kit shows the shape of cholesterol very well. In fact, that's what it's designed for. It's designed to show the shape and the relative distances apart within the molecule of different atomic centers. The FISA kit is only one of many different kits. You're familiar with the orbit kit. I've got here a partially constructed model of cholesterol using your orbit. What's missing is a double bond. You're going to construct a double bond. You need 2 centers with 3 prongs on them to form 1/2 of the double bond. And now with the orbit kit, to make a double bond, it's precisely what one does. It puts another bond on the top. So there is the double bond. We'll fit that onto the molecule. So you can see that goes in there. That goes there. Now all that remains to do is to put the hydroxyl group in its correct position. And there is another model of cholesterol. The orbit kit is very similar to the FISA kit in that it shows you the overall shape of the molecule and the distances apart of the atoms. But this is only an approximate model. If you want to know exactly interatomic distances, then you go to a very beautiful but very expensive set called the Drying models. Now this Drying model is designed with very high tolerances. The distances between the atoms have been very accurately measured, so that this gives a very good idea of the distance between any 2 atoms. Again, this is cholesterol with the OH group at the back and the double bond at the front and the 4 rings. I'd like to show you just one more of this type of molecular model. And this is a Benjamin model of cholesterol. Again, it gives exactly the same information as the other molecular models that we've just seen, the FISA, the orbit, the Drying, and now the Benjamin. So these tell us the overall shape and the distance apart of atoms. But sometimes you need to know how close atoms get together. Now you can't really do this with these because atoms are represented essentially by points. There is another set of models, the Catalin models, and this is actually again a model of cholesterol, but this time you can see how close the atoms get together, and this in some cases is very important to know. So both types of molecular model, the framework and the space-filling models, rely to a large extent on the tetrahedral carbon atom. What What I want to do now is to look a little more closely at the consequences of having a tetrahedral carbon center. This is a model of a tetrahedral carbon atom surrounded by 4 different groups: a hydrogen, a fluorine, a chlorine, and a bromine atom. But what you're looking at isn't reality, it's a mirror image of that molecule. But can that mirror image have a separate existence? Well, let's see. Well, yes, it can. Here's the molecule, and here's its mirror image. They both have the same 4 groups around them, but are they identical? Let's test. If they are, we can superimpose the 2 molecules. So now, I've got the fluorine atoms above one another, and the chlorine atoms above one another. But the bromine here is above the hydrogen here, and similarly, hydrogen above bromine. Well, let's put that right. So now the bromines are above one another, and so are the hydrogen atoms. But now the chlorine is above the fluorine. In fact, I just couldn't superimpose these 2 molecules because they have a very special relationship to one another. They're non-superimposable mirror images, and we call them enantiomers. And each compound is called chiral. The chiral carbon atom appears many times in nature, particularly in the amino acids. This is a model of an amino acid. It's got a chiral carbon atom surrounded by the 4 groups: carboxylic acid, amino, hydrogen, and in general an R group. In this case, because it's alanine, it's a methyl group. All the naturally occurring amino acids are chiral, with one exception. And that is glycine. Now glycine, again, has the carboxylic acid group and an amino group, but this time 2 hydrogen atoms. So this carbon atom only has 3 different groups around it, so it's not chiral. This molecule is in fact superimposable on its mirror image. If you don't accept that, then I'd like you to make models to check for yourself. In fact, all the naturally occurring amino acids except glycine have got the same configuration about this central carbon atom. The carboxylic acid group is always here, the amino group here, hydrogen, and the R group. Let's have another look at that on a different model. The carboxylic acid group coming out, the amino group here, the R group here, and the hydrogen on the top. Now if we look a little more closely at this particular model, we'll see that it bears a very strong relationship to the sorts of projections we use in the text. Here's a wedge to illustrate the carboxylic acid group coming out towards you. The dotted line represents the R group going back, and the hydrogen, carbon, and amino groups are all in the plane of the paper. So this is a representation of your projections. Well, chirality is only one aspect of molecular stereochemistry. Chirality is concerned with the way that groups are arranged around a central carbon atom. There is another aspect called conformation. This is a model of ethane with 2 carbon atoms and 6 hydrogen atoms. It's a flexible model, flexible molecule. It can take different shapes, different conformations, which is different arrangements of atoms. This particular arrangement is called the eclipsed conformation, because this front hydrogen atom is eclipsing the rear hydrogen atom. And similarly, these 2 at the front are eclipsing the back ones. If we rotate through 60 degrees, we get to this conformation, which is called the staggered conformation, because of the regular way in which the hydrogen atoms are arranged. But what would we see if we were able to look at a molecule of ethane at very low temperatures? Well, as it got very cold, it would exist mostly in the staggered form, just wobbling a little. And as it warmed up, it would start to undergo internal rotation about the carbon-carbon bond. The molecule of ethane has a certain potential energy in the staggered conformation, and we have to put more energy in as the eclipsed form is reached. As the rotation continues, energy is released until the next staggered conformation is formed. This is a cyclical process, and the graph of energy against conformation looks rather like a smooth sine wave. Now we'll look a little more closely at the two main conformations in ethane. In the staggered form, the hydrogen atoms are as far apart as they can get, given the constraints of a fixed bond length. But when we get to the eclipsed conformation, these hydrogens are now as close together as they can get. Although this particular model doesn't show it, there is an interaction between these neighboring hydrogens, and that means that to attain the eclipsed conformation, we have to put energy into the molecule relative to the staggered conformation. Now let's look at the way that the energy changes as the molecule rotates about the carbon-carbon bond. At very low temperatures, the molecule exists predominantly in the low-energy staggered form. And as the temperature increases, rotation will start. Here you can see the rotation from a variety of angles. At room temperature, there's so much energy available that the molecule is undergoing very rapid internal rotation, as well as spinning, tumbling, and translational motion. In ethane, there's only one eclipsed conformation and one staggered conformation. Let's have a look at a bit more complex example. 1,2-diiodoethane. 2 iodine atoms, 2 carbons, and the 4 hydrogen atoms. This conformation is an eclipsed conformation. Let's look at its Newman projection. This is called the syn-periplanar conformation. It's called that because both iodine atoms are on the same side of the molecule, so it's syn, and there is one plane running through this iodine and the 2 carbons and the other iodine. So they're all in a plane, so it's syn-periplanar. Now if we rotate through 60 degrees, we go from the eclipsed conformation to a staggered conformation. This staggered conformation is called the synclinal conformation. Syn, again, because the 2 iodine atoms are on the same side of the molecule. Clinal, because there's one plane running through this iodine and the 2 carbons, and another plane, an inclined plane, running through that iodine and the 2 carbons. So that's the synclinal conformation. Well, let's rotate through another 60 degrees, and we reach another eclipsed conformation. Now this isn't the same as the first eclipsed conformation, because the 2 iodine atoms are now at 120 degrees to one another. This conformation is called the anticlinal conformation. It's anti now because the 2 iodine atoms are on opposite sides of the molecule. and clinal again because of the two inclined planes. Let's move around a little more, another 60 degrees, and we reach a staggered conformation. Now, using the rules that I've just said, what do you think the name of this staggered conformation is? Well, the two iodine atoms are on opposite sides of the molecule, so it's anti, and there is a single plane running through the four atoms, the iodine, two carbons, and the other iodine. So yes, it's an anti-periplanar conformation. This is a staggered anti-periplanar form. We concentrate here mostly on the staggered forms. As the molecule rotates about the carbon-carbon bond, it passes through the eclipsed anticlinal conformation and then onto another staggered conformation, a synclinal conformation. Now look, as it passes through another eclipsed conformation, the syn-periplanar conformation, onto the third staggered conformation. I'd like you to make models to confirm that these two synclinal conformations are in fact different. So, there are three staggered conformations, one anti-periplanar and two synclinal. Now let's return to the model. Now what we're going to do is we're going to look at and see how the energy of this molecule changes as it rotates about the carbon-carbon bond, and as these very bulky iodine groups get closer and further apart. If we start at 0 degrees, that is when the two iodine atoms are eclipsed in the syn-periplanar conformation, they're as close together as they can get, and that's a high energy conformation. As we rotate through 60 degrees to 60 degrees, we reach a minimum at the synclinal staggered conformation. Rotating through another 60 degrees to 120 degrees, we reach another eclipsed conformation, the anti-periplanar conformation. That's an energy maximum, but not quite so high as the first maximum, because the iodine atoms are not as close together as they can get. Continuing on for another 60 degrees to 180 degrees, that's where the iodine atoms are as far apart as they can possibly be in the anti-periplanar conformation, and that is the lowest energy minimum. Going back through 60 degrees onto 240 degrees, we reach the eclipsed anticlinal conformation again, and that's another maximum, the same as the other anticlinal conformation. Going on another 60 degrees to 300 degrees, we reach the second synclinal staggered conformation, which is another energy minimum. And continuing on to 360 degrees, we get back where we started from, to the syn-periplanar highest energy conformation. In this program, we've shown you the way that molecular models can be used to illustrate both conformation and configuration. There are many instances within this course where you will be expected to understand such concepts, and we hope that you'll now go away and use your own orbit kit to help you to understand the stereochemistry of organic compounds.